darn. Yes, thank you for reminding me. Well, let's see. Yeah, I'm okay. We just started recording because the old man forgot. I apologize to the people who watch this as recording. About a third of the class watches this on YouTube. Missed the first half. It wasn't very exciting anyway. You'd have slept through it. Okay. Thank you for reminding me. Yes, Ethernet has a broadcast address. It's a particular address. It's all 1 bit that it sends out, and that means everybody should receive this packet. The Ethernet hardware looks at the address as the packet comes in. If it's the packet if it's the address for this device, then it receives it and passes it on up. If it's not, it just drops it, with the exception, of course, of broadcast addresses. Whenever it receives a broadcast, it passes it up to the next layer. So in order to send a packet from one computer to another, you have to use the hardware address, basically the Ethernet address. It won't get there using the internet address. It has to know the hardware address. So if you have the internet address of the device and you know that it's on your own local network, which you can tell from the internet address, the first so many bits of the destination address and your address, they match, it means it's on your network, in which case then you have to find the hardware address to send it. That's done using the ARP protocol. ARP is a pretty simple protocol. It simply sends a broadcast to every computer on the same network and says, are you this internet address? So everybody gets the packet, it's a broadcast, they all receive it, and if, in fact, that is their internet address, they send back an ARP reply saying, yes, here I am, and here is my physical address, my MAC layer address. If it's not their IP address, then they ignore it. But it requires a broadcast to everybody, and everybody responds. And then when the computer gets that answer, it stores it away. It has an ARP cache where it stores all the addresses that it's figured out so far. So it keeps that. So next time it wants to send another packet, it doesn't have to do the ARP. It already knows what the address is and uses that. There is an attack called ARP poisoning. ARP poisoning is when a different computer responds. So you go out there and you say, who's this particular IP address? And before that computer can, or maybe after that computer responds, then the malicious computer response is, here, I am that computer. Well, your computer will save that response away, and then when it wants to send a packet to that address, it will send it to the physical address of the malicious computer, because that's the one who told it what address to use. And then all the packets go there. Typically, this forms what they call a man-in-the-middle attack. I don't know why it's not a woman-in-the-middle attack, but it's a man-in-the-middle attack. And then, so your packets go to the interceptor, and then the interceptor will usually send them on after carefully reviewing or recording them. So that's ARP poisoning. There are a couple ways to defend against ARP poisoning. Your ARP cache can be initialized with a series of static read-only entries. Now, you can say, here are the hardware MAC addresses for these particular internet addresses. And then it doesn't look them up, and it won't change them. ARP is not a very smart protocol. Anytime your computer gets a response or an ARP reply saying this IP address goes to this hardware address, it saves it. It doesn't matter if it sent one out, it just saves it. I got a reply, I will save it. They weren't thinking security when they made that, but they weren't thinking security way back in 1970 when they made this, 1980. That wasn't being thought of. Now it's very important. So on your local network, and again, ARP is only going to attack you if you're on your local network, because it has to be on the local network in order to send that ARP reply, which only goes on local networks. But if there's another computer, if you're in the lab and some other computer can send out a reply, all right. So it's valuable to put a static address in the table to start with. When your system boots up, it knows where is your primary router. How do you get to that primary? This is going to need to know that anything going off your local network has to go to your router. What is the MAC address of your router? If you just figure that out, once, put that in the file, mark it as read-only, and then it will never get changed. That's where you're usually sending the packets. At least in my computer, very rarely do I send a packet to my wife's computer or to my phone. I'm sending the packets to the internet, and it goes over the router. There's also IP version 6, the Secure Network Discovery Protocol, SCND, the SEND protocol, that is much more secure and allows different computers to share hardware addresses in a safe, secure manner. Well, some computers, particularly phones, will randomly make a MAC address from a choice of them. That way, you never know what they are. They go and they turn them on, they make up a MAC address, so they're not the same next time. Well, it doesn't matter, because if you go to a different location, a different connection, it's going to use a different, the old address doesn't matter anymore because you're not connecting through that. So it works fine. That way you don't know who they are. Edward Snowden, you might remember several years ago, was the person who leaked a whole bunch of information from the NSA to WikiLeaks, and then ran off to foreign countries, and now I think is living in Russia because nobody else likes him. Well, if he lives in any other country that has a agreement with the United States, they will extradite to the United States. But he said that they have systems to track mobile devices. Well, of course they do. NSA doesn't have to do that. Google will do it for you. Yes, Google keeps track of where you're going. Who needs the NSA? Okay. Internet names. We talked about physical address. Talk about internet names. Internet names, you've seen these things, www.acme.com. They're usually in this form. On the right is a type. What network type is this? There's .com.edu. I'll talk about that and many others. The organization, which might be NCAT or whatever you want. Then there's the host, is on the far left. That is the computer name. What computer are you going to? Popular computer name is www, because that would be their web server. There's also several others. Subnets, which may or may not occur, that's the name of the organization, or excuse me, well, name of some group in there, or a smaller network. Here at A&T, we don't use subnets in the name, but we do have the big network is divided into many subnets. Once upon a time, when they were organizing the internet here at A&T, remember I've been here for 30 some years, so I know, it was going to be a right to left was edu ncat department computer. So it would be, my computer was williams.comp.ncat.edu. But then they change of administration, and somebody decided to do it differently. I'll note the names are case insensitive, the upper and lower case. A lot of people think they're case sensitive. Nope, they're not. But if you have a URL, which is the internet address / file names, the file names may be case sensitive. Okay, names come from, or signed, you can go out and buy them, but they all actually come from the Internet Corporation for Assigned Names and Numbers, ICANN. And ICANN is an organization out there that does that. There are lots of types. Here is just a small list of the many types. You got edu for educational.gov, .mil for military, .name, you can get your own, ends in .name, or you've seen those. Country codes are often used. With the .gov, some of this here in North Carolina, it would be dmv.nc.gov. So it would be the government, North Carolina Department of Motor Vehicles. I think their network runs slow, the rest of it does. And then you have country codes. A lot of stuff with country codes, it'll be .us or .ca for Canada, not to be confused with .ca for California, but and then there's like .de for Germany. DE, well, yes, for Deutschland, it's in their native language. There's all sorts of them. Some of them have been used. I'm trying to, yes, .nf. Last year, my class network, was in .nf, which is some Pacific Island nation. I don't know, but they make their money by selling their IP address. Okay. Domain name servers are those machines that convert between IP names and IP addresses. So it's just a database. And a whole bunch of IP addresses and a whole bunch of names. It's a hierarchical database. There's lots of these things out there, all sorts of domain name servers. Every network must have its own domain name server. It's a requirement. So your internet service provider must have a domain name server. And so when your computer boots up through a process called DHCP that we will not talk about, Dynamic Host Configuration Protocol, it goes out and says, what should my address be? Who, and it also gets information like, who's my router? Where is my domain name server? And so your internet service provider will have to give an answer. Question. Every computer domain, a domain would be type.organization. So ncat.edu is a domain. Acme.com would be a domain. Every domain must have its own domain name server. And we'll see why in just a minute, because you have to get to it if you want to find out the address. Yes, so it's pretty simple. There's a format of a packet that a computer sends to the domain name server, and it replies saying, here is the address, or I don't know, go ask over here. Or it can ask them. All right, let's see if people are awake, and we'll try this one. Anybody need a card? Everybody got the card? Oh, everybody get the card. And hold your card up if you got it. Okay, hey, hope that's the right answer. Yes, almost everybody answered C, which is our gives an invalid MAC address for a given IP address. Very good. Okay. Well, just yeah, that was it. Yeah, everybody knew that. Yeah, you're all paying at least some attention. Okay, domain name servers operate in a hierarchical structure from the right to left of the address system. At the very top is the group like the .name or .com or .edu. There's a server out there, and the .com server knows all the everybody's address that's .com. They know the name, they know the address, the IP address of the domain name server for every domain that ends in .com. And there's one for .edu and all the others, .museum, what have you. .online, you're in our class, the IP address ends in .online. So you don't know where it is. I think it's in England. Oh, okay. So there's an order. If it doesn't know, it asks. Let's look at the example I have for how that works. Makes it clear. All right. Here we are. me.ncat.edu. And I want to know what is the IP address of www.acme.com. And in C or in Java, there's a function called getHostByName, and it returns the IP address of that. So you call that function in your program, and of course, your browser down in the bowels of your browser, it's calling that function to figure this out. So your computer sends a request off to the domain, your local domain name server. So from here on campus, ncat.edu, it sends it to the domain name server .ncat.edu. I don't know what it's called, but I call it DNS.ncat. Okay, that one, if it doesn't know, it will send a request up to the .com root because it's okay. I need to know .com. So it sends up to the root. It says, where is this .com server? And it says, oh, I know the .com server. It's over there. So it sends it back. So then my domain name server here at A&T sends a request over to the .com domain name server, which it knows. It sends a request back to my server. Then my domain name server sends a request to the acme.com domain name server. And again, I said all domains have to have a domain name server. This is why, because if you want to know where www.acme is, you have to send it to acme.com's domain name server. So it sends a request, and of course, it replies back to the A&T domain name server, which at last tells me where it is. Now, it saves that information because you don't want to do that every time you have to send a packet. That network could never get anywhere. So it remembers the IP address for each IP name. Note that, of course, it's not using MAC addresses. It needs, for MAC address, it needs to know the MAC address of your local router in order to send it to the domain name server. Okay. Now, it caches this information. Your computer saves this information, and the domain name server caches what it learns. So let's say here's another example. This time you want to go to ftp.acme.com. Last time we were going to www.acme. It's a different computer, maybe. So we have that name. We're going to get there. So we send a request off to the domain name server. We're assuming, of course, we did this after going to www.acme.com. Now, my domain name server has been here before. It knows where the domain name server is for acme.com. So it directly sends a request to that one. That one, of course, must know the addresses of all the computers in its domain, sends back the request, which sends it back to me. Got that? So it doesn't have to go all around. Now, all along the way, you can do an assortment of network attacks on the domain name server. When they first built this thing, like many other parts of the internet and computers, they weren't thinking security at all. They didn't put any security in this. So it was very easy for somebody to make a computer and act like a domain name server and start replying to these messages and sending false information so that all sorts of computers all over the area would be getting false information. And it happened a lot. So users could by falsifying information in the domain name server, get you to send information to their computer. So a malicious person might falsify information up to the domain name server and say, oh, google.com is my computer, or amazon.com is my computer. And everybody who's going to amazon.com comes to your computer, and you can decide what to do with that information. Okay, another clicker question just to see if you're awake. Okay. Yeah. There we go. Oh, that's weird. All right, C is a very popular answer. Yes, that's what it does. Domain name server converts IP names, the names that humans can understand, to IP addresses. Doesn't do anything with MAC addresses. And you can see that was really popular. Okay, they have come up with security for domain name servers because it's so very important. There's the Domain Name System Security Extensions, DNSSEC, which is updates to the domain name server protocols that provide additional security. Basically, it uses digital signatures, uses the standard public key infrastructure system and puts digital signatures on the end. And so each domain name server has a certificate, and it sends that along with the packet. So when you get it, you check the hash of the packet, check to see if it matches the domain name, domain that sent it. And you were supposed to get it from dns.acme.com. Is this the proper certificate for them? If it is, good. And you only have to have the certificate authorities certificates in order to validate it, because remember, in certificates, the address comes in it. Okay. So that helps a lot. There have been, nevertheless, a number of big name, very vicious attacks against some of the webs. There was one against Google. They were attacking domain name servers, trying to poison. Well, yes, because a lot of things go through Google to start with, redirecting. It lasted for 6 months before they killed it, and it was peaked out at 2.5 terabytes. These are distributed denial of service attacks, which we haven't talked about. We will talk about a little bit later, but that's where you get a lot of computers all at once to participate in sending requests to the server. So a lot of them are sending false information. Amazon got one for 3 days. They were easy, 2.3 terabits per second. This impacted a lot of course, impacted lots of people. AWS is Amazon Web Services. Amazon Web Services is a cloud service provided by Amazon. Amazon, of course, has to have lots of great big computer servers to keep their company alive, and they have extras, and they sell time on the extra servers for cloud computing, and they're one of the major cloud providers. Here's an example of the attack. The network traffic is just going along, not much happening, and then pow, all of a sudden, it jumps up to 1.35 terabits per second. That's a lot of data. And then drops down, oh, maybe again. And so that was an attack. And it's very hard for these systems to support that kind of traffic. Also, that level of traffic tends to block out other users. Networks come in two flavors: connection-oriented and connectionless. Typical example is a telephone call is connection-oriented. You have to dial or press the number, call somebody, and they pick up, and then that's it. You can just talk. Everything you say goes to the other person. Everything they say comes back to you. It's well, typically one-to-one, although you can do a broadcast to people. But you provide the address in the beginning, it makes that connection, and you go on. You also know when you make the connection that you've got the right address. Otherwise, you get an error telling you the address is incorrect. A letter is different. You write multiple letters, even if they're the same person. You put the address in every letter, put a stamp on each one, stick them in the mailbox. They're all routed across the post office system, or not, thanks to the pride of Greensboro, but we won't go into that. And then they hopefully get the other side individually. Each one has it. Now, the letters may get there in order or may get there out of order. Sometimes letters get delayed, sometimes they get lost. And so they get different than phone calls. So when you send it, you don't know if it's going to get there. It may, after a while, tell you, no, it didn't get there. But it's connections. Every packet is separate, like every letter is separate. The Internet Protocol is a connectionless best effort network. That is, it's not you don't set up a connection. Every packet is connectionless. Just sends it out there and hopes that it will get there. It's the best effort. I hope it will get there. It should, normally does. Sometimes it doesn't, but usually it gets there. So you worry about that later. Again, so internet addresses are used to route packets. Sometimes packets arrive out of order. Sometimes because different packets may arrive through different routes. Some of them go over here, some of them go over there, and they get there in different times. Sometimes they get lost. Sometimes they get corrupted. By the way, they call the packets datagrams. As you send those packets over various physical networks, each physical network has to put another set of packet or headers and stuff around it. So if you're on one computer and you want to send it to your router, you got to put that Internet Protocol datagram inside an Ethernet packet, send it over there. The router gets it, takes it outside of the Ethernet packet, looks at it and says, oh, I know what to do with this. Wants to send it to another router. That other router might be connected by a fiber optic FDDI link or something. So it puts it in that protocol, sends it to the other one gets there, takes it out of the FDDI, looks at the packet, says, oh, I know what to do with this. They might put it in different Ethernet packet. So each time the packet is taken out and wrapped in another packet of that particular local network until it finally gets wherever it's supposed to go. When it finally gets to the destination, you got to figure out what program is supposed to get this packet. Because you're looking at your computer and you might be running Zoom and sending out zillions of packets to the Zoom server. You might be surfing the web, looking at something on Amazon, Googling something, looking on Wikipedia, sending email, all these network-based activities all at once, and packets are going in and out of your computer. Well, you have to sort them out as to what packet goes to what application. That's done through port numbers. Port number is a number. It's a 16-bit number, so you have 65,000 different possible combinations. Some people have to be reminded that ports do not refer to plugs in the back of the computer. Ports are just a number. So the internet address comes with the number. Sometimes you have to put the internet address :number. Here's an example. You got www.acme.:4321, and that means send it off to this computer to that particular port. Now, there are assigned ports for well-known applications. HTTP goes to port 80. HTTPS goes to port 443. So it gets there. And the internet stack, when it gets in, there's a field that says what port is it supposed to go to, and it gives it to the appropriate application that registered that port. FTP has one port, and Telnet has another port, and all these things, systems have ports. There are many well-known ports that have been assigned by ICANN, the number of people, and so each group has ports. You don't see them too often used because most organizations use the default port. Oh, well, there we go. There are higher level protocols, internet protocols on one, and then on top of that, there are transport layer protocols. The one that everybody knows is TCP, the Transmission Control Protocol, and that's very popular. There's also the User Datagram Protocol, which is very popular. A lot of packets going out there across the network, and the User Datagram Protocol, people just don't know about it as much because everybody knows about TCP/IP. They say it as if it's 5 letters all at one piece, but it's TCP, like /IP. IP is the Internet Protocol. TCP is a transport protocol that sits on top of it. Interesting thing to know about UDP. UDP does almost nothing. UDP uses Internet Protocol packets, adds very little more functionality to it. But it does almost nothing, but it does nothing very efficiently because it doesn't add any features. It can do that very quickly, very easily. TCP, on the other hand, adds a bunch of extra functionality to the IP packets. Where I mentioned Internet Protocol is connectionless, best effort, so is UDP. TCP is connection-oriented, and it corrects errors. So when you first want to create a TCP connection, you have to do a connect, and it sends a packet out to the other side saying, I want to connect. And it responds saying, okay, and there's a back and forth going, saying, I'm going to connect, and all sorts of other parameters that I won't go into, but it specifies that the connection is going to form. And then whenever packets go across, they're all numbered. So when the other side gets them, if they're out of order, it can reorder them or at least fix that problem. If they are corrupted, that is, a bit gets changed, it will detect it, or ask it be resent. So it tries to get all this correct. Both of them are full duplex, meaning they transmit in both directions at the same time. TCP is point-to-point, meaning one computer is talking to one other computer. UDP can be whatever you want. Typically, it's one computer to another computer, but you can broadcast one computer to many computers, or many computers can try sending things to one computer, whatever you like. TCP is stream interface. At the low end, you send information to TCP. You give TCP chunks of data in big pieces, 64K chunks if you want. And then, because the Internet Protocol doesn't work in 64K chunks, it breaks it up into pieces, ships it to the other side, puts it back together on the other side, and gives it up to a higher level, fixing all the lost pieces. But it's stream-oriented. You can request, give me the next 5K pieces. And if you have 64 cents, it'll give you the next 5K. It remembers how much you got. Whereas in UDP, it sends a packet. And the other side can get a packet. And if you send a 1K packet and you say, oh, give me 100 bytes, you get 100 bytes, but that's it. You don't get the rest of them. You asked for the packet, you get what you asked for. So TCP is connection-oriented, reliable protocol, whereas UDP is connectionless, best effort, packet at a time type protocol. As you might guess, HTTP uses TCP, many other web-based applications. There are a lot of applications that use HTTP and the web that are not things you see on your browser. There's an awful lot going on the different computers, sending information to other computers, particularly business-to-business communication. That's going over TCP and HTTP that you don't see. Others like Telnet or FTP, file transfer, those are all basically anything that has a lot of transfer and you want reliable communication. Now, UDP sends DNS requests. You want a DNS request, you want to know the IP address for an IP name, you send one packet off, and it gets back. If you don't get a result real quick, you send it again. Maybe you send a couple the first time and hopefully you get one of them back. But because it's going to be the same thing, it doesn't matter if you ask multiple times, you're going to get the same answer. UDP is often used for streaming video, streaming audio, because it's very efficient. The human ear doesn't really care if a milliseconds worth of music is dropped out. You won't really notice. My ears won't notice. Maybe yours will, but my ears certainly won't notice. And so it's very efficient. TCP corrects errors. If something gets lost, something gets corrupted, it will try to replace that or get the packet to be retransmitted. This causes a delay. And some people don't want that delays in their communications. They want it to be nice and smooth. So they use UDP. You don't get the delays. You don't do the retransmissions. You may lose a packet here and there. Oh, well, live with that. If it gets really bad, you might have to throw it and start. It usually, any audio or streaming, usually collects a bunch of packets and then starts displaying the information, or putting it through the speakers for audio display or on the screen for video display, and it keeps a buffer. So it's out there. Taking them off the network as fast as it can, puts them in one side of the queue. On the other end of the queue, it's pulling off the packets and displaying them on the screen and on the speakers. Sometimes the network slows down and that queue gets down to 0 and you see the little circling message saying it's buffering or something, it's waiting. That's because the network slowed down slower than how fast the information was being displayed to the user. It has to wait for it to catch up. There are other protocols out there besides TCP and UDP. There's Internet Control Message Protocol. That is a control that is for controlling the network, particularly for, I'll go to some use in just a minute. It helps solve network problems. If there is a problem, it's reported to other computers on the network through ICMP. Some of the uses, there's a ping protocol. I don't know if you ever use ping. You can go ping space www.ncat.edu, and it won't work because it's an ICMP, and the A&T servers filter out all the ICMP. They will not allow the ICMP to go through the routers. A lot of routers filtered out because it's mostly for local. But you can ping other computers on your local network. Sometimes you might want to know what route is the packet taking. There's a command for that. You can ask it how a packet's getting there. It's kind of fun to look at. If you're sending a packet downtown, you might find it's going through Georgia or someplace because that's the central router, and you can do that. Trace route is the command. You send that. It will tell you it does that by sending ICMP. There's a TTL, time to live. As you send a packet out, it has a TTL number. Every time it goes through a router, it decrements that TTL number. If the number ever gets down to 0, it figures that packet is lost. It's been circling around through the network, and it drops it. Or sometimes it drops it and sends a message back, an ICMP message saying, hey, I just dropped this packet. Something's going wrong. And there's several other requests you might do. If you send something to a router and that's not the right router to send it to, it will send an ICMP message back. Also, that router will forward it to the right router, so you don't need to know, but it's helpful. Of course, ICMP has a threat. You don't want other computers messing up your network control, redirecting things to different routers that don't exist or that aren't real routers. And as I mentioned, a lot of systems don't forward ICMP packets because they wouldn't allow external people to send control messages into your network. You probably don't want that. Another question, just see if we're alive. most people said D, which is too bad because the people online, they were awake. They knew the answer was TCP. Answer is B. No, B. Only B is connection with TCP. Internet protocol is connectionless. UDP, which does almost nothing, runs on top of the Internet protocol, and it is also connectionless. So the answer is B, TCPs. All right. While we're share the results, you see. Okay, stop sharing. Let's take a short break. I want to talk a little bit about stop at a time now. All right. Okay, let's see if we can get this to work. Do the online people see number-based conversion quiz results?
Yes.
Yes.
Great. All right, this works. Okay, I have taken everybody's score from the server, determined whether they were certificate students, whether they were master's students, or they're undergrads, which took a lot of time for me because I should have asked you or something. Anyway, next time I won't ever do that again. But a lot of people forgot that it was time. People went out there and did it. Somebody took 22 minutes. They got a very good score percentage-wise, but they got a big negative score. Because remember, it's the percent right minus the number of seconds past the limit. So some people tried. I'm impressed by the student who did the quiz 71 times. They did eventually get 100. But it took them a while. Then you can do it as often as you like. Somebody did. Some people did it many times, but they forgot to put the name in there. They had the name. If you do it without putting your name in there, I don't know it was you. Here are these scores. This is not an evenly distributed. A lot of hundreds. Yes, many people did it till they got 100. Some people, it took them a lot of practice. Some people, no, 2 or 3 times they got 100. Then there was people who did pretty well, 80 to 99. And then there are bad, scores. People did, low scores. And then there are people who got very bad scores. And there were 9 students who had negative scores. 9 students who took too much time. And if you, if you're more than 100 seconds past the limit, then no matter how many questions you got right, you're going to get a negative score. And some people just didn't do it right. They had far too many scores. So we have a number of bad scores there. I do not want to have a lot of bad scores. So Ken the Kind is going to allow you to do that for the rest of this, until Thursday. So if you got a bad score, you can go out and do it again. You only get a maximum score of 85, though, if you do it. So if you got a really miserable score, and all the scores are out on Blackboard, do it again, and get a score up to 85. If you've contacted me earlier about problems, you can get up to 100. But other than that, yes. So those of you who didn't understand it had to be fast, now know it has to be fast, or you're not going to get this counts as a score. I gave everybody a 1 if they had a negative score. I'm not going to give you a negative number that will average in with destroy your exam. No, I gave you a 1, which is a little bit better than a 0 if you didn't do it. But you can do better. Yes, just try. You may not have to try 71 times. Maybe 65 times would be enough. But just keep trying it. We'll practice, and you'll get better and better at it, and you'll be able to get a good score. So please go out there and get a good score. Any questions about the quiz? All right. More. Okay. All right. Online, you're seeing transport layer security?
Yes.
Thank you. Okay. Moving on. Got 15 more minutes. Okay. Again, there's the lower level is the physical layer. Then you have the media access control layer, the network layer, and then the transport layer. The transport layer, by the way, is the end-to-end layer, and there are security for that. There's transport layer security is what puts the S in HTTPS. So you can go out there, and if you're using HTTPS, other protocols, Telnet uses transport layer security in order to security. It's a hybrid network. We've talked about this before. Yes, it starts off using RSA to transmit a randomly generated AES key, goes to the other side, and then after that, they use the AES protocol. Okay, I think we talked about that. Anybody should know about that. Okay, firewalls. Firewalls are a network device that typically connect between the big evil internet and your hopefully safe local network. And it's usually part of the router that goes between those two devices, and it filters out packets that you, for some reason, don't like or don't want. So you have here we have the internet, here you have your local network, and the router has a firewall that goes there. You can also have software firewalls in your computer. They can be hardware or software. Typically, most systems have both. AT&T certainly has lots of firewalls operating at multiple levels. They filter out a lot of junk. There's a lot of junk out there in the network. I think I have some statistics on that later on. And again, you can have filters at multiple layers. At the network layer, you can filter out based on the address. Circuit level layer, based on the port. What is this protocol? What are you trying to do? Application layer, again, that's like HTTP. There are checks for that. And then there are proxy servers and NAT, network address translation servers. Basically, they're packet filtering. Packets go into the firewall. The firewall looks at all sorts of parts of that packet. It looks at the destination address, looks at the source address, looks at the protocol you're using. The higher level filters will look at information to see if this is a known attack. If it is, it's just going to drop it and never gets into your network. You have to define what you want for an internet protocol. So firewalls require configuration. And again, you can filter based on also source address, where did it come from, which can be forged. So you can say, I don't want packets from this address, but it may or may not actually come from that address. Where it's supposed to go to, port numbers, protocol, all those things can be used for filtering criteria. Application layer filtering, again, decide what is it doing, whether I want to allow it. At the lower levels, you can say, I'm going to allow this connection. Okay, I think I just said you have to configure these things to whether you want to allow things. On commercial networks, or here at A&T, we've got somebody whose full-time job basically is to configure that firewall and make sure that we're blocking all the nasty stuff. For your home network, you can usually take the defaults. And they provide what they call perimeter protection because it's filtering what's coming into your network. Now, if you have a bad actor in your local network, then you're in trouble because what's going around your local network does not go through the firewall. The firewall typically goes between the outside and then your network. Now, here at A&T, we have multiple subnets, and there is a certain layer of filtering between the subnets. So if you have something nasty on one subnet, it will not flow to other portions of the A&T network. Industries may have a area that is covered by their firewall, and then parts of their network that is not covered by that firewall. Or there may be a stronger firewall and a weaker firewall, and inside that area, it's referred to usually as a DMZ or demilitarized zone. You might put your public servers. Your web server might be in the DMZ. So packets coming in go through one level of filtering, to that firewall, goes to your web server, and then the web server goes back. If you're trying to get to other portions of your network, you have to go through a second firewall, which has much more stringent requirements. So that way, you can access the web server, but you don't have access to the inner workings of that network. So DMZ is a very popular concept, having multiple firewalls and putting some servers outside the inner network. Your Microsoft and your Windows allows you to configure your firewall. You can say, I don't like that computer. I don't ever want to get a packet from it. It's probably dangerous. And you can turn it off. You can go out to the control panel or go out to set up security firewall and start changing it. Be careful what you do, because if you turn off certain things, it won't work very well. You can specify exceptions you can allow. There are general rules that say never for this, and you say, oh, but I do want these. Things are ordered, and so order is important. It is difficult sometimes to know a bad packet when you see one. How do you know that this is going to be evil? At the higher levels, when malware starts to come out, there are a big system in the United States, across the world, to recognize malware and then send out alerts to various organizations around the world, but send out alerts to other organizations. Eventually, everybody learns about this malware, updates their firewall to stop that malware. Email is filtered. I might notice it's not filtered nearly as much as yes. Back in 2007, 90% of all the email was junk. Spam was real popular. Might not have noticed because firewalls are filtering out huge quantities of email. Only 3% of the email actually went through the firewall. Most of it was junk that you never saw. I mean, if you did see it, your inbox would fill up instantaneously. It was just huge quantities of spam. Well, that's down to now 45%. But still represents a huge quantity of junk going across the network. Network's getting clogged up with packets that nobody wants. The firewalls are filtering out, the users never see them. So before you even get spam email, it goes in your junk folder. It might be filtered out by the firewall. The stuff that's filtered by the firewall does not appear in your junk folder. It doesn't appear in your computer at all. Your computer never even knew it happened. I might point out that there's 145 billion spam messages a day. That's a lot of stuff going across the network. Network address translation is a feature for security. It also allows you to have more and more computers on our network. It's a pretty simple concept. Your router usually does network address translation. Your router shows only one address to the internet. You may have a dozen computers on the other side of your router, but only one address shows up on the internet. Everything that goes to your network goes to that one address. The router gets it and looks at the port number and then says, oh, going to this port is supposed to go to that port on that computer, and then changes it to a local address. So your computer has local addresses, and then there's a global address on the internet. There's a bunch of addresses that never appear on the internet. They're only for intranet or internal use. Yes, your question.
Yes, you say the router shows only one address.
Yes.
Yes, you said, so even multiple computers will use one address.
Yes, all the computers each have their own individual address and then they send something to the router. The router then changes the addresses in the packet, changes the sender address to be its one address, but changes the port number too. Keeps a table of the port numbers. It's, oh, and since there's up to 65,000 port numbers you can use, it starts using them. And if something comes in for that port, it goes, oh, let's see, it was this number, looks on its table, goes, oh, it's supposed to go to this particular computer on my intranet inside at that particular port number. Changes the destination address and port number so it goes to the right computer on your inside. So people on the outside don't know anything about your inner workings of your network. You don't know how many computers are there. You don't know what their addresses are. And typically you cannot send a packet to it. If you establish a connection with TCP going out to someplace, the router remembers that connection. When packets return for that connection, it goes, oh, it allows it. But if you start getting packets for a connection you didn't set up, well, it just drops them. It doesn't allow things to come in that aren't expected by your network. There are Ethernet addresses. No, well, this is wrong. That, who wrote these? That's supposed to be internet addresses, not Ethernet, internet. That's wrong right there. Who wrote this? I did. Okay, internet addresses on local use. There's a 192.168.0.0 all the way up to 192.65. There's a 10 dot, so there's 16 million addresses you can use. That should be enough for most internal networks. Very few networks have more than 16 million computers in them, so that should work. So you have a network address translation router, things as AT&T does. If you look at your addresses in your local computers here, they're usually 10 dot something. And that's, of course, a local address. As you send it out, it translates that into the address of the router, goes back and translates it back to your local computer. Nobody knows. One of the big advantages of that is that IP address version 4 only have 32 bits. It's only about 2.14 unique addresses. That's just not enough these days. It seemed like a huge number of addresses back in 1980 when they had only a couple dozen computers out there on the network. So it was fine. But now that we have networks all over the place, they're on your phones, there are billions of people, there's 8 billion people in the world, 2.2 billion addresses isn't enough. So we have network address translation. So here at AT&T, we only use one network address in Ethernet. Well, excuse me, on the IP. Internally, there's always, I couldn't remember, Internet Protocol version 6 has great big addresses, and that allows us to have more. Okay. I'm going to pass on this, and on the rest of it, we are, let's see, we are on slide 80 of 93. We're not going to get to the next 13 slides in the next 3 minutes. So we will save that stuff for next time, which is pretty good because I copied it from the slides for next time, thinking I would get done early. All right. So this is fun. But since we're here, we have a question. Let's do the question. We have a chat. Right. The answer to this one is all the above. I'm just going to give this one to you. It's all the above. Firewalls keep things out. Network address translation keeps out unwanted packets. And of course, the DMZ keeps things, allows things to the outside network, your web server, maybe your FTP server, but keeps them away from the inner workings. Okay, so that's it for today. I apologize for not starting the recording earlier. Look on the slides. You will come back on Wednesday. Remember, you have till, yes, you have until Thursday at noon to redo the number-based conversion if you want to. If you got better than 85, well, then it doesn't do any good because the best score you can get is 85. So if you got 100, don't do anything. Let it stay. If you got 90, well, too bad. Stay with your 90. All right, that's it. See you on Wednesday.